Hello everyone, myself Darshan Lakde, and I am a student of MIT Academy of Engineering doing my BTech in Electronics and the Telecommunication. And this is the presentation on the implementation of FIR filter using DSP processor, guided by Professor Nutan Bansode. So the outlines of the presentations are the problem statement and the objective, introduction, FI filters, different types of windows, implementation, result, formulas, calculation, conclusion, and the references. So moving forward, our problem statement is to implement an FI filter using TM-S320F28335 DSP processor. And the objectives of the PPTs are to study different types of windows, to analyze the noisy signals, to calculate the desired frequency response coefficient, to calculate window coefficient, to calculate output signal y of n, to analyze the output signal, to design and implement the filter using dedicated DSP processor. Introduction. In nature, no signal is totally clean. Each signal has one or more types of distortions. Before they may be utilized for the application, this distortion must be eliminated. This is where filters are used. Filters totally alternate the undesired frequency from the signal those we get from our surroundings. Many input signals can be filtered by one digital filter without replacing the hardware. Digital filters are characteristics like linear phase, which is not possible to obtain in the case of analog filter. In the implementation, we are going to use the TMS320F28335 DSP processor. It is a floating processor which is well suited for the performing heavy calculations. FI filter. FI filter stands for the finite impulse response. These filters are called as non-recursive filters because they do not use the feedback. In order to design such filter, various Windows functions are available. The Windows method require minimum amount of the computational effort, so it is simple to implement. Also, for given window, maximum amplitude of a ripple in the filter response is fixed. Thus, stop band attenuation is fixed in the given windows. While designing a particular filter, first the specification of the required filter have to be defined. This specification may vary depending on the application of filter. Only if we know the requirement frequencies to pass through, we can move ahead. Once a cutoff frequency is known, we can move ahead and calculate the desired frequency response. SD of n, taking inverse Fourier transform of the response, we can calculate h of n. In this, n stands for order of the frequency, which will be mentioned in the specification. Substituting the different values of n, we will get the different values of h of n. Different types of the windows. First one is the rectangular window. It is the simplest window function available. Its magnitude is 1 for the range. N is equals to 0 to the m minus 1, where m is the length of the filter. The function of the rectangular window is given by omega wr is equals to the 1 for n is equals to the 1 to up to the m minus 1. The Hanning window. The Hanning window is named after the inventor Von Hahn as the shape of one cycle of the cosine wave with one added to it, so it is always positive. The function is given as whm is equals to the zero point 0.5 in bracket 1 minus cos in bracket 2 pi n in bracket n minus 1 for n is between 0 and m minus 1. Hamming window. Hamming window. This is the another window function popularly used. The Hamming was named after R.W. Hamming. It was recommended for the smoothing the truncated auto covariance function in the time domain. Its function is given as WHM is equals to 0.54 minus 0.46 into cos of 2 pi n minus 1 for n is n between 0 and m minus 1. Black window function. In Blackman window function, we find one more addition term in the comparison with the Hamming and the Hanning window because of the addition cosine term. Side lobes are reduced further. Window function for Blackman can be given as WB is equals to 0.42 minus 0.5 cos 2 pi n minus 1 plus 0.08 cos of 4 pi n minus 1. The implementation, now just let's see about the implementation result. Waveform of the input noisy signal. Take Fourier transform. This signal will given as an idea of frequencies present in this signal and its magnitudes owing to Fourier transform plot of CC S, we can directly plot the Fourier transform of the noisy signal. The frequency plot of input signal. From the frequency plot, we can analyze that our noisy signal has roughly four frequencies. Components, the frequency plot has frequency in Sz on the x-axis. Waveform of the output signal. Once output signal has been calculated, we plot it using the graph features of CCS. We find that the output is sinusoidal wave corresponding to the fundamental frequency. The frequency plot of the output signal. Now we plot the frequency plot of the output signal. It's show that the filter has only fundamental frequency, and it has heavily attenuated rest other frequencies. The above steps showed the design of the low pass filter with the cutoff frequency of 50 Hz. Formula and the calculation. Newly modified filter design equation will be HD is equals to the E minus 5 J W minus 5 pi pi in between 0 and 0.1 pi, and the pi is greater than or equals to W and lesser than 0.1 pi equals to 0. Otherwise, the next to calculate the HD of n, for we will use the same formula as used for in 9. Only this time the main integral will be break down into the two integrals as given in the below. Conclusion of the presentation. Efficient hardware implementation of the filter using a digital signal process is done. From the result, we can conclude that the final output signal has only the fundamental frequency. All other frequencies have been heavily attenuated through the filter algorithm. It is also observed that the DSP reduces the tedious calculation and the computes the convolution very quickly and saves a lot of time. Digital signal processor has a wide range of use, and one of them is creating filtration. The DSP can filter real-time signal using ADC and DAC and output the process result on an oscilloscope. Thank you.